Hello, and welcome back to the anatomy portion of the Certified Ophthalmic Assistant lectures. In this video, we'll be covering the cornea, sclera, uvea, angle structures, and the lens. This segment is definitely longer than the last, so let's just get right into it. The cornea is a clear, transparent structure with a shiny surface. It has a convex surface that acts as a powerful lens. Most of the eye's refraction takes place through the cornea. Although the eyeball as a whole increases a little less than 3 times in volume from birth to maturity, the cornea is relatively large at birth and is fully developed by age 2. The cornea is thicker at its periphery than at its center, measuring 1 millimeter and 0.5 millimeters respectively. It can be divided into 5 distinct portions: the epithelium, Bowman's membrane, the stroma, Descemet's membrane, and the endothelium. The epithelium is the part of the cornea that is usually injured by superficial abrasions or small foreign bodies. It is 5 to 7 cells or 50 micrometers thick and is composed of non-keratinized stratified squamous cells. It serves as both a barrier and a refractive surface. The epithelium can regenerate rapidly without leaving a scar, but injury to the deeper structures usually results in the formation of a corneal opacity. Bowman's membrane consists of randomly oriented collagen fibrils of greater periodicity than the stroma. When we say periodicity, we refer to the tendency to recur at regular intervals. Bowman's membrane is acellular and about 10 micrometers thick. It has no regenerative capabilities and its function is currently unclear. The stroma accounts for 90% of corneal thickness, measuring about 950 micrometers at the periphery and about 450 micrometers centrally. It consists of 200 to 250 evenly spaced type 1 collagen lamella, which are oriented at right angles to their adjacent lamella. It is 78% water. Remember how I said the cornea can be divided into 5 distinct portions? Well, it turns out there may be a sixth. A 2013 paper published in Ophthalmology suggested the existence of a pre-Descemet's layer, measuring at a hypothetical 15 micrometers. It is currently unconfirmed and its potential significance unknown. Descemet's membrane measures 3 micrometers thick at birth and 10 to 12 micrometers thick in older adults. It is composed of type 3 collagen. This layer is very elastic and retracts if cut. Descemet's membrane forms the basement membrane of the epithelial cells. The endothelium is a 4 to 6 micrometer monolayer of 500,000 cells. These cells gradually decrease with age. There's currently no known mechanism of attachment between the endothelium and Descemet's membrane. The endothelium is responsible for maintaining detergescence, or relative dehydration, of the cornea. No regenerative capability of this layer has been shown in humans. Corneal edema can occur when contact lens material, overwear, improper cleaning, or improper fit do not allow sufficient oxygen to reach the cornea. The junction of the cornea and sclera is demarcated by a gray, semi-transparent area called the limbus. This transitional zone is only 1 millimeter wide and marks the point of insertion of the conjunctiva. The cornea contains no blood vessels and is completely nourished by 3 sources: a plexus of fine capillaries at the limbus, the tear film, and the aqueous humor. Now that we've wrapped up the corneal layers, let's move on to the sclera. The sclera forms the posterior 5/6 of the eye's protective coat. The anterior portion is visible as the whites of the eye. In children, the sclera is thin and appears bluish because the underlying pigmented structures are visible through it. In older adults, it may become yellowish due to the deposition of fat. Attached to the sclera are all extraocular muscles. Through the sclera pass the nerves and blood vessels that penetrate the interior of the eye. At its most posterior portion, the site of attachment to the optic nerve, the sclera becomes a thin, sieve-like structure called the lamina fibrosa. It is through here that the retinal fibers leave the eye to form the optic nerve. The episcleral tissue is a loose connective and elastic tissue that covers the sclera and unites it with the above conjunctiva. Unlike the sclera, the episcleral tissue is highly vascular. The uvea consists of 3 structures: the iris, the ciliary body, and the choroid. The iris is the most anterior structure of the uveal tract. It is perforated at its center by the pupil. The iris has many furrows and ridges on its anterior surface. It contracts in response to bright light thanks to a flat muscle called the sphincter pupillae, which is buried around the pupillary opening. Dilation of the pupil results from the relaxation of the sphincter muscle and by activation of the iris's radially oriented dilator muscle. Expansion and contraction of the iris forms circular pleat lines or furrows visible on its surface. Additionally, numerous white zigzag lines are formed by the blood vessels of the iris. Between the iris and cornea is a clear fluid called the aqueous humor, which occupies the anterior chamber of the eye. The ciliary body is directly posterior to the iris and adherent to the sclera. It is plump and thrown into numerous folds known as ciliary processes. This portion is only about 2.5 millimeters in length and is responsible for the major production of aqueous fluid. The ciliary body is generally triangular, with its shortest side anterior and a flat posterior portion. The inner part of the short anterior side enters the formation of the angle of the anterior chamber. The iris takes root from the ciliary body's middle portion. The equator of the lens sits only 0.5 millimeters from the ciliary processes and is suspended by fine, ligamentous layers called the zonular fibers. Most zonular fibers of the lens originate from the ciliary body. On the outer side of the ciliary body triangle is the ciliary muscle, which lies against the sclera. Contraction of the ciliary muscle releases the tension of the zonular fibers, controlling the size and shape of the lens. This in turn allows the anterior surface of the lens to bulge forward and increase its power. Therefore, the ciliary muscle directly controls the focusing ability of the eye. In children, the ciliary muscle is extremely active and the lens is easily deformed, which accounts for its powerful range of focusing abilities. The ciliary muscle does decline with age, however. After 40, it becomes weaker and the lens is less able to change shape. This makes focusing it near, or accommodating, difficult. We know this difficulty accommodating as presbyopia. The choroid is in direct continuity with the iris and ciliary body and lies between the retina and sclera. The choroid is primarily a vascular structure. Its main function is to provide nourishment for the outer layers of the retina. The angle structures are formed by the tissues posterior to the cornea and anterior to the iris, with the aqueous humor intervening. Included in the angle structures are the root of the iris, a portion of the anterior surface of the ciliary body, a spur from the sclera, the canal of Schlemm, and the corneoscleral trabeculum. Aqueous humor leaves the eye by filtering through the crevices of the trabecular meshwork, which consists of tiny pores. It is through these pores that the aqueous humor travels to reach Schlemm's canal. From Schlemm's canal, the aqueous humor leaves the eye from the aqueous veins penetrating the sclera. Obstruction within the trabecular meshwork or the angle structures, whether it be by iris or scar tissue, results in increased intraocular pressure and glaucoma. The final structure we'll be covering today is the lens. The lens of the eye is a transparent biconvex structure that lies between the iris and vitreous. Only the portion of the lens directly behind the pupil is visible. The center of the anterior surface of the lens, known as the anterior pole, sits only about 3 millimeters from the back surface of the cornea. The diameter of the lens is about 9 to 10 millimeters. Its peripheral margin, called the equator, lies about 0.5 millimeters from the ciliary processes. It is attached to the ciliary processes and to the posterior portion of the ciliary body by the zonular fibers. The lens is surrounded by a transparent, highly elastic envelope called the capsule. In infants, the lens material here is soft and putty-like. With age, it tends to grow harder, especially towards the center of the lens. The nucleus of the lens is the harder central portion found in adults 30 and older, while the cortex is formed by the outer lens fibers. The harder nucleus occurs as a result of normal developmental growth of the lens. As new lens fibers are produced, the older fibers are pushed more toward the center and are compressed in a concentric fashion. This constant compression of lens fibers over a period of years eventually produces the nucleus. Once again, I'd like to thank everybody for sitting through this with me. I know this is a lot to get through. The next video, I'll be covering the vitreous, retina, optic nerve, visual pathway, and ocular muscles, which will actually conclude the entire segment of anatomy, at least in the textbook that I'm using. In the future, I'd like to make these videos a little longer, so we'll be moving on to physiology, optics, pharmacology, and microbiology, which is actually going to cover all of the basic sciences that you'll need to know when going into the rest of your COA. So just like last time, if you have any questions, comments, concerns, anything that you would like to be addressed, anything you'd like to see expanded upon, please do not hesitate to comment, to let me know. I'm working through this with you guys and I know how stressful it is, so I want to do my best to make that easier on everybody involved. Um, I hope this is a good study tool for you, and once again, best of luck moving forward with your COA. Thank you.